Good morning. Myself Srishti Choudhry, working as lecturer in Electronics and Communication Engineering branch in GPGC Patiala. Today we are going to discuss upon multi-stage transistor amplifiers. Now, what are the multi-stage transistor amplifiers? What was the need of multi-stage transistor amplifiers? Why they emerged? And different types of multi-stage transistors amplifiers are going to be discussed in the lecture today. Now, the first basic question that arises, that what is the need of a multi-stage amplifier, why we need a multi-stage amplifier. The amplification obtained from a single stage transistor amplifier is inadequate to drive the output devices. For example, your loudspeaker works as a output device. The amplification that is obtained from a single stage transistor is not adequate so that it can drive the output device. Thus, to amplify the signal to required level, number of amplifier stages are used in succession. These number of amplifier stages can be 2, 3 or 4 as desired by the user, such that output of one stage is coupled to the next stage. They are designed to be placed in a succession, one after the other. So, when they are placed one after the other, the output of one stage is given to the next stage as the input. That's how the multi-stage amplifier are constructed. Now, so we have now a simple definition of what a multi-stage amplifier is. A transistor circuit in which a number of amplifier stages are used in succession is called a multi-stage or cascaded amplifier. As we can see in this block diagram, here we are having the number of stages. Stage 1 with the gain G1, stage 2 with the gain G2, stage 3 with the gain G3, and we can have number of stages up to n levels, that can stage n with gain n. Here at the input of stage 1 we are having the input signal. This input signal is amplified by stage 1 with the gain 1. After the amplification, it is given to stage 2 with gain 2. So, output of first stage, that is the output of stage 1 with gain 1, is now input of stage 2 with gain 2. Again, stage 2 amplified this further, give to stage 3. Stage 3 amplifies the signal further and provides to the next preceding stage, until unless you are having the last stage that provides the final amplification, and at last you are having the load circuit. Now, when these stages are linked one after the other, that is, that are placed in succession, they are not directly linked. The interaction between the first stage and the next stage or the preceding stage is done by a coupling. That is the interaction of one stage and the second stage. When you have to interact the two stages, that is known as the coupling. The first stage is coupled to the next stage, that is the termed named. In multi-stage amplifier, output of one stage is connected to input of next stage through coupling device. Now, these coupling devices performs the following functions, that is, they transfer only AC output of one stage to input of next stage, and they block the DC components, that is, no DC components are allowed to pass from first stage to second stage. Only AC signal or AC output of first stage is allowed to enter to the next stage. Now, the coupling is done to interact the two stages, before and preceding stage. Now, according to which type of coupling you are using, you are having the different types of coupling and different type of amplifiers. If you are first is the RC coupling, if you are using that first stage should be coupled to the second stage using a RC coupling, the name of the amplifier is RC coupled amplifier. Next is the transformer coupling. If the first stage is coupled to the next preceding stage through a transformer, then it is known as the transformer coupling, and it is coupled through a transformer coupled amplifier. And the last one is third one, direct coupling. Here the first stage is directly coupled to the next stage, your preceding stage, without any other component, so why its names are direct coupled amplifier. Now, dealing with multi-stage amplifiers, we have to consider some basic parameters for multi-stage amplifier. The commonly used or parameter is gain. We all know the gain is the ratio of output to the input of an amplifier, which is known as the gain, and it is generally represented by G or A. It can be a power gain, voltage gain or current gain, depends which gain you are calculating for your particular circuit. If you are considering for parameter power, it will be power gain. If you are considering the voltage, it will be the voltage gain, and if you are considering the current, it will be a current gain. Now, Now we have to calculate with an example the gain of a multi-stage amplifier. Here again the block diagram shows a multi-stage amplifier with n stages up to the stage n, starting with stage 1, proceeding with stage 2, stage 3 up to stage n, with individual gains G1 as the gain of stage 1, G2 as gain of stage 2, G3 as gain of stage 3 and Gn as the gain of stage n. Now for example, let V in be the input of your multi-stage amplifier. This V in is given to your stage 1, V in is amplified by stage 1 and this amplified output is the input of your G2. The amplified output is V in into the gain of first stage, that is G1, that is V in into G1 is the output of stage 1, but this is the input of stage 2. Similarly for different stages we are having, at last we are having output as V in into G1, G2, G3 into Gn. So it is given as, let V in be the input of first stage, G1, G2, G3 are the gain of first, second and nth stage of amplifier. Overall gain of multi-stage amplifier is the product of gains, that is G1, G2, G3 up to Gn as the number of stages you are having. However, in the practice the overall gain is always less than the product because the loading effect of the next stages affect the overall gain practically. Now this is given a simple derivation of your multi-stage amplifier gain, as I have described that the output of first stage is G1 into V in, second stage input of preceding stage. Now G1 into V in is the input of your second stage, that is multiplied by gain of second stage, that is the output of your second stage now. Similarly for third stage you are having G1 into G2 into V in, that is your input to your third stage, and now output for your third stage is the input multiplied the gain of your third stage, that is G1, G2 into Vn into G3. Similarly for your n stages. Now overall gain we have discussed, that is the ratio of V out by V in. So substituting the value of this V out we have calculated, that is Gn into G1, G2, G3 into V in. Substituting the value, we are having gain is equal to G1, G2, G3 up to n stages, that is Gn. So similarly in a simple statement we can specify that the gain of multi-stage amplifier is simply the multiplication of individual gains of your stages, as G1, G2, G3 are your individual stage gains, G1 for stage 1, G2 of stage 3, G3 of stage 3. Now second parameter that has to be discussed is decibel. While considering the gain, there was no unit. No unit is assigned to gain of an amplifier, since it is the ratio of output to the input of an amplifier, as we have derived that V in is cancelled by V in, so there is no unit for your gain, where input and output are of similar quantities having same units. Telephone industry however proposed a logarithmic unit named bell or a decibel after Alexander Graham Bell. Now if we have to consider a power gain, again it is the gain simply is output upon input. If we have to consider the power gain, then it is your P out upon P in, and if you are having to consider it on the logarithmic term, that is log 10 P out by P in into bell. For practical purposes, bell is quite large unit, therefore 1/10 of this unit is considered more convenient. So 1/10 is your decibel, 1 bell is equal to 10th of decibel. Therefore power gain if considered in decibel is 10 log 10 P out P in into T. Similarly voltage and current gain, we have considered that in logarithmic, when you are having considering the log, the square is multiplied further by the term. Here you are having voltage gain 20 log 10 V out by V in. Why this 20? Because when power is considered as a voltage or current, that is V square or I square. So the square is in log in maths, that is in forward multiplied by the unit. So 2 into 10 log 10 V out by V in, that becomes 20 log 10 V out by V in dB. And similarly for current gain, you are having 2 into 10 log 10 I out by I in, that is 20 log 10 I out by I in. Now why dB? Why we are considering are units in dB, not in other simple in. Overall gain can be determined by just adding them. We have discussed that your amplifier gain is G1 into G2 into G3. For example, the gain of your all the stages, your 3 stages is 10. If the gain is given, you have to multiply all the gains, that is 10 into 10 into 10, that is a complex. But if you consider in a logarithmic term, you have to simply add it. As we all know, while considering the log, your term simply add, that is log of 10 plus log of 10, that is of stage 2, plus log of 10 the stage 3, they are simply added. But if they are not in decibel, they have to be multiplied, and multiplication is a complex procedure as compared to your addition. Again, very large gains or linear scales can be denoted by small figures. For example, you are having a very high gain of 1000 and 2000, that can be simply denoted by small figures when we are considering in a decibel. Now, third parameter is the frequency response. Frequency response is a curve drawn between voltage gain and the signal frequency of an amplifier and is known as the frequency curve. Here we have given a diagram for your frequency response. The x and y axis shows respectively their voltage gain and the frequency. The voltage gain of amplifier is not constant. Here we can see that voltage gain is not constant, it varies with the signal frequencies. As your signal frequency is increasing, your voltage gain is also increasing. But at a particular point, that is your resonant frequency, your gain is maximum. After this point, if your frequency increases further, your voltage gain decreases. Now, why it is so? As reactance of capacitors connected change with signal frequency and affect the output voltage or gain. We all know your x is equal to 1 by 2 pi fc. As your frequency increases, your reactance decreases. Your change in reactance affects your signal output voltage or gain. Now, the last parameter is your bandwidth. We all know bandwidth is the range of frequency over which gain of an amplifier is equal to or greater than 70.7% of its maximum gain, and it is known as your bandwidth. Also, we have to calculate it in terms of your voltage gain. Now, in terms of your voltage gain, we have defined that it is equal to or greater than the 70.7% of its maximum gain. So, if you have to consider the fall in voltage gain from maximum gain, that is 20 log 10 gm, that is your maximum gain, upon fall in voltage, that is 0.707 gm, that is 70.7% is calculated, that is 0.707 gm. This gives you value of this. After taking the logarithmic term, after doing the calculations, you are having the end result at 3 dB. So, now another definition of your bandwidth is, it is the range of frequency over which your gain falls by 3 dB, that is your bandwidth. Therefore, bandwidth can also be defined as range of frequency within which voltage gain of an amplifier falls by 3 dB of its maximum gain, as described in this figure. This is the maximum gain and this is your fall in dB, that is 70.7%. At this point, this is your bandwidth. When your gain falls by 3 dB, this is the fall of 3 dB denoted. Now, coming to the coupling. These are two single stage amplifiers. Here two single stage amplifiers are shown. This is one single stage amplifier, this is another single stage amplifier. Multi-stage amplifiers are what? When one stage is connected to another stage. The first stage, in precision you are having the another stage, and if you want to increase the number of stages, you can place one another stage after this, and in between you are having the coupling. Now, these two stages are interacted through coupling, and this coupling, the type of coupling which you are involving or which you are following, gives you different types of multi-stage coupled amplifiers, as we have discussed: RC coupled amplifier, transformer coupled amplifier and direct coupled amplifier. Now, these three types of amplifiers are going to be discussed in detail now. The first is your RC coupled amplifier. In RC coupled amplifier, as this first stage is coupled to the next stage through R and C. Now, as your circuit diagram shows, this is your first stage and this is your second stage. The coupling is done through a coupling capacitor. Here at the output you are having a coupling capacitor that is connected with two shunt resistances of your next stage. So this R and C is a coupling between these two stages. That's why it is named so RC coupled amplifier. So now we can answer this, why RC coupled amplifier or RC coupled multi-stage amplifier is named so. Output of first stage appears across collector resistance RC, which is coupled to the base of next stage through coupling capacitor CC. As coupling from one stage to another stage is achieved by coupling capacitor followed by a connection to a shunt resistor, it is named as RC coupled amplifier as shown. Now you are having different components involved in your circuit. We have role of each component, as your input capacitor CE allows only AC signal to flow and it blocks your DC signal. The emitter capacitance, that is CE, offers low reactance path to the signal. Now this low reactance path is required so that your gain is not lost of your stage. You want a particular gain, the gain should not be lost by your particular circuit, so CE offers a low reactance path. DC power supply is employed here in circuit. The resistance R1, R2 and RE. All this provides potential divider biasing and stabilization network. The stabilization network is required so that your Q point, quiescent point or operating point should not be affected. That is, it establishes a proper operating point to get faithful amplification. RE, that is your emitter resistance, it reduces the variation of your collector current with temperature. As we all know, transistors are affected by your change in temperature or variation in temperature. So RE reduces the variation of the current with respect to your temperature. Collector coupling capacitor, that is CC, that allows amplified AC signal of one stage, as shown in the diagram of your first stage, is coupled to the next stage through this coupling capacitor. So it blocks DC and again allows only AC signal to pass on. Now coming to the working, at the input you are giving the signal, AC signal is applied to the base of the first transistor, and through transistor action this transistor is amplified, and this amplified form appears across the collector resistance RC of your first stage. This amplified signal is fed to the base of next transistor through coupling capacitor CC. Now second stage further amplifies the signal and overall gain is increased. Now why overall gain is increased? You have provided the amplification twice. Now here we are considering a two-stage multi-stage amplifier, two-stage RC coupled amplifier. Two amplification stages are provided. The signal that was to be amplified only by one stage, here it is amplified by two stages. You are having two amplification processes, so the gain is increased. The overall gain is less than product of individual stages because load resistance of each stage decreases due to the shunting effect of input resistance of next stage. We have considered in the block diagram and the circuit diagram. As your first stage is coupled to the next stage through shunt resistances, the shunt resistances decreases your gain. Again, this is the circuit diagram of your RC coupled amplifier. Now coming to the frequency response, we have studied what is the frequency response. It is the graph drawn between your voltage gain and the frequency. Now here also you are having three cases of a low frequency, mid frequency and a high frequency. Considering these three different cases, at low frequencies the gain of your RC coupled amplifier is small. Why it is small? As a part of AC output of first stage is lost in coupling capacitor, which offers very high reactance at low frequencies. At low frequencies your reactance is very high, as nu Xc is equal to 1 by 2 Fc. Now Fc is very low, at low frequency Xc is very high, and this high Xc offers very high reactance. At low frequency CE offers high reactance and could not shunt the emitter resistance RE. So these are two main factors why your gain is small at the low frequency. Now coming to the mid frequency, at the mid frequency gain is constant. Now why this gain is constant? Because we are having two reasons. One, that provides the increase in your gain and another contradicts it by the decrease in gain. So, the gain that was increased by a level is decreased by the same level, providing a constant gain. As frequency increases, the reactance of CC decreases, which tends to increase the gain. At low frequency your gain was small because your reactance was very high, but here now as your frequency increases, the reactance of coupling capacitor decreases, which increase your gain. But this decrease in reactance produces higher loading effect. The loading effect is increased, which decreases the gain. So, the gain which was increased now was decreased by the loading effect of the circuit. Thus, both factors maintain a constant gain. Considering the third case, that is your high frequency, here the voltage gain drops. Why it drops? The reactance of coupling capacitor is very small and it behaves as a short circuit. This increases the loading effect of next stage and reduces your voltage gain. Capacitive reactance of base emitter junction is low at high frequency, which increases base current. This reduces current amplification factor and thus voltage gain. Now, here as the frequency response curve is shown, we are having three cases. This was your low frequency, this was your medium frequency, and at last you are having the high frequency. At low frequency your gain is low, at medium frequency you are having a constant gain, and at the high frequency again your voltage gain drops. So, this is the frequency curve or frequency response of your RC coupled multi-stage amplifier. So, what are the advantages of your RC coupled multi-stage amplifier? First, here the components used are very commonly available. So, the cost is low because of low cost of coupling capacitors and resistances. The capacitors and resistors are easily available in the market, and again these components require very less space. So, your RC coupled multi-stage amplifier occupy less space because of small size of resistors and capacitors. So, again due to the same reason the weight is less of your multi-stage RC coupled amplifier. You are having the better frequency response. The various stages are DC isolated. This features facilitates the biasing of individual stages. DC isolated means you are blocking the DC and you are allowing only AC to pass on. The various stages can be similar, hence the design of amplifier is simplified. Now, coming to the disadvantages of your RC coupled multi-stage amplifier, the gain is smaller because of loading effect of the next stage. The impedance matching is poor in case of your RC coupled multi-stage amplifier. Impedance matching can be simply understood by a basic principle that the signal that is provided at the input is equal to the signal that is at the output, that is P in is equal to P out. But in case of your multi-stage RC coupled amplifier, it is not. So, impedance matching is poor. The coupling capacitors influence the responses of the amplifier. A great number of biasing resistors is necessary, and the application of your RC coupled multi-stage amplifier is it is used as voltage amplifier as initial stages in your circuit. Now, coming your second coupled amplifier, that is your transformer coupled amplifier. The difference here occurs only at the coupling. Here we can see you are having the two stages. This is the first stage that is similar as we have done in the RC coupled, and this is the second stage. These two stages are similar. The difference occurred at this coupling, how the first stage is coupled to the next stage. Here the first stage is coupled through a coupling transformer to the next stage. You have removed the coupling capacitor here. In RC coupled amplifier you used a coupling capacitor at the output of your transistor T1 that was coupled through shunt resistances, but here that coupling capacitor is replaced and you are having a transformer that is coupling your first stage to the next stage. So, again output of first stage is coupled to second stage through the transformer. So, it is named transformer coupled multi-stage amplifier, and the other components have the same role as discussed before in your RC coupled amplifier. The other were your C-in. C-in provides only the AC to pass on and it blocks your DC. Your R1, R2, RE and DC battery provides your stabilization and potential divider biasing, so that your operating point is not affected. Again, RE provides your reactance path. All the components have the same role as that was discussed before. Now coming to the working of your transformer coupled amplifier. When an input AC signal is applied at the base of first transistor, again an amplified AC flows through the collector circuit of transistor and hence through primary of the transformer. Amplified output is transferred to secondary side of coupling transformer and is fed to the base of transistor of next stage. As you have employed your transformer, the amplified signal is provided at the primary of your transformer. Through the transformer action, your signal passes from primary to the secondary. After it is arrived at your secondary side, this signal is further provided to the base of the transistor of next stage, or you can say the second transistor T2. Now this signal is further amplified and is provided at the output of your second stage, and this is obtained again through the across your secondary terminals of your output transformer, as you have employed a second transformer at the second stage. There is no coupling capacitor in circuit. DC isolation is provided by the transformer itself. As you are having no coupling capacitor, this your transformer provides the isolation, DC isolation itself. One disadvantage of this transformer coupled is that you are using a transformer, so when a magnetic is produced along this transformer, you are having a humming noise due to this transformer coupling. Now, how this provides the impedance matching? RC coupled amplifier were poor in your impedance matching, but your transformer coupled provides your excellent impedance matching. Impedance matching is the practice of designing the input impedance of an electrical load or the output impedance of its corresponding signal source to maximize the power transfer or minimize reflections from the load. So, in simple, impedance matching is that your maximum output is delivered to your next stage. The input that you are giving should provide the maximum output at the next stage with minimum reflections from the load. That your load should affect your minimum signal. So, RL connected across the secondary of the transformer with turns N1 and N2. RL resistance from primary side will be different. Now, as you change your position to locate your resistances, your resistance value will change. So, your resistance from primary side has to be calculated now. RL dash by RL, this RL dash is the resistance from the primary side, that is equal to V1 by current I1 into V2 by current I2. After solving this, we are having the value N1 by N2 into N1 by N2. So, we provide N1 by N2 square. Therefore, your primary side resistance is equal to N1 by N2 square into RL. Now, taking an example so that we can understand this impedance matching clearly. For example, we want to match a 16 ohm speaker load to an amplifier so that effective load resistance is 10 kilo ohm. We have to match, we provide the impedance matching so that a 16 ohm speaker, that is your load, it is following as a load, and it has to be effective load resistance with 10 kilo ohm. Substituting these values to this formula, that is your RL dash equal to N1 by N2 square into RL. Now, your RL dash is 10 kilo ohm, N1 by N2 square, and your this RL is 16. Solving this, you are having the ratio of 25:1. So, to match 16 ohm speaker load to this particular load, we want a transformer coupling that should provide this ratio 25:1. Now, your next transformer coupled amplifier frequency response. Frequency response is poor, gain is constant over small range of frequency. Output voltage is equal to product of collector current and reactance of primary. At the output, you are having V into IC, that is the output voltage is equal to the product of collector current and reactance of primary. collector current is denoted by IC, reactance of primary is denoted by XC. So output voltage is V out is equal to IC into XC. As your frequency varies, your reactance varies. Frequency is low, reactance increases. Frequency high, your reactance decreases. This affect your output voltage. So at very small range of frequency, you are having a constant frequency response. At low reactance of primary falls, resulting in smaller gain. As we know that X is equal to 1 by 2